Okay, hello. So now Magdalena Nowak will talk about PySpark.
Hello everyone, welcome to my talk, Make the PySparks Fly. I'm Magdalena Nowak, a few words about me. Currently, for another month, I'm a technical lead at Relayer, which is an industrial IoT company. I have 10 plus years of experience in data science, machine learning, and I actually studied mathematics. So that's the way I landed in data science. If you want to reach out, here's my LinkedIn page. Okay, so when I started this, planning this talk, I wanted to give a brief introduction into Spark, how Spark actually works. And then I thought it would be like more meta to actually give you the sort of introduction usually data scientists get when they start using Spark, which is none. I don't know how many of you are data scientists and how many of you have used pandas. Yeah, like a lot of you used pandas. So when a data scientist learns from management that they are going to actually do big data now, and sometimes it's even not the sort of big data that fits in an Excel, they just hear, okay, so the transitions should be super easy because you're already using pandas and Spark is very similar. I don't know how many of you have been to the Polar's talk yesterday, but yeah, the introduction is similar. So here's how it's done in Python, PySpark, how it's done in pandas, and that's basically what people get. And how it actually works when they get started. So these are two flows that I've seen in many projects. Usually they converge to either one or the other. So first is just running SQL, basically SQL queries on Spark. And the other way is actually trying to write in PySpark, yes? So you use those selects, you use those wheres. And then what like 99% of data scientists do is this. So this is the extent of PySpark that they learn. But then, yeah, maybe that's not a bad idea, right? But usually you hit this thing, and I hope I can actually play the video now. Yeah. Okay, so then it ends up with Googling, like PySpark to pandas, and you can see what are the usual things people Google about to pandas. It's either out of memory, memory error, limit, very slow, not working. Actually, this time I Googled it, it cut off all the Java errors that you actually get underneath, yes? And when a Python person sees this Java error that's connected to about nothing in their mind, they were lost. And all of this happens because here you see the actual doc string for the toPandas function, toPandas method. And what most data scientists don't actually read is, oh, they just read it, returns the pandas data frame, that's amazing. And they never read this note at the bottom because they never learned how Spark actually works. And they don't really know what means like all the data is loaded into the driver's memory. That's like, you know, like black magic for them. It's supposed to work. What they know about Spark is that it works fast, and is great for big data, yes? So when they get those big data tables from their big data database, they just want to do what they know. And is it actually a bad thing that this is what they do? Like, I don't really think so, because sometimes you actually want to do something that's not possible in PySpark, or maybe you just don't know it's possible. Or maybe it's not possible in the PySpark version you are using. And while updating functions locally, like updating packages locally is very easy for us. If you have like on-prem cluster, you need to actually convince somebody who handles this cluster to do an upgrade. And that's sometimes not an easy task, and I know it from experience when I was using like PySpark 2.2 for years, even though I knew 2.3 was already available. But also just rewriting your Python code to pure PySpark can be quite difficult. I remember a situation when I was doing code review for one of the guys on my team, and I saw, well, spoiler, UDF function to do something in pure Python. And I said, actually, maybe you could, I think this could be done in PySpark, because this was just some data transformations. And like one day later and 30 lines of code later, he said, whoa, what an amazing exercise. I've learned so much about random weird functions from PySpark. But it was like, maybe his time wasn't really best used in this case. And in general, when you have a huge Python code base and you want to move to PySpark, yeah, it might be difficult to, not just impossible to do it like in reasonable time, but imagine telling your stakeholders, oh, so I need a month to just, transfer from this one framework to another, but I swear it will work awesome. Yeah, like in my experience, it's not that good. And well, something that I don't know if you've seen all those memes about how you just import pandas as PD, voila, you're a data scientist now. But actually, pandas, when you're a data scientist, pandas is your comfort zone. And while it's fun to step out of the comfort zone, when you need to do things fast, you usually stay in it. When you need to be sure that something works, you also stay in comfort zone. And the thing is, like I mentioned, like people say, oh, PySpark is just like pandas for big data. And you will just learn those. Like you, instead of doing square brackets, you will do select statement and it will be just the same. And without investing actual time into letting people learn how Spark and PySpark work, yes? So now we know why we do what we do, but what can we actually do instead? So this will be a non-comprehensive guide. Why non-comprehensive? Because I will be on purpose skipping some stuff. Like I will not mention like anything about Spark ML. Let's assume that the models we're handling cannot be actually done with Spark ML, even though it made great strides in the recent years. It's still not that good. I will not mention anything to do with RDDs, and I will sure as hell not mention anything about Pandas API on Spark, which was introduced for people who didn't want to ever leave their comfort zone. This is not what the talk is going to be about. So let's start with the easy stuff, the stuff that actually data scientists sometimes get to learn. Because naturally, you want to do something that cannot be done in pure PySpark, and you learn that there's a possibility of defining a user-defined function. You might know this term already from SQL or whatever. And it's just easily you can write a function in a language that you already know, which I guess is Python. And you can extend PySpark functionality, yes? And you can actually skip this 2-pandas step to do your job right on the executor, yes? But yeah, so there's the, what's the rest of the talk about if this is the solution? Okay, so here's the cons column. So Python UDFs are very inefficient and they are the source of a lot of bottlenecks in code flows, yes? So why does it happen? Because people just learn it's inefficient, whatever, because it's Python and they just have this, idea of Python being inefficient and think that's the source. But actually the biggest issue is the data movement. Because when you're on the executor, you have a JVM there, and you need to move data somehow to Python. And this serialization and deserialization going through this pipe from JVM to Python is really costly. And it's also one row at a time. So you can imagine that that's not very efficient if you have millions of rows. And all the optimization built into PySpark, into Spark itself, is just gone because it's not usable when you have actually UDFs. Yes, this is something you design yourself. So still, how would you go about creating such an inefficient but UDF? It's quite easy, yes. So for the rest of the talk, just when you see SF, it's PySpark functions, ST is Spark types. And creating a UDF is just actually sticking a decorator on the function or wrapping the function with this UDF function. So here we have the easiest example, like adding 1 to a number. And it seems quite nice. Yeah, it's done easily. You just add this UDF decorator. You specify the return type because it ignores some of the things we like about pandas. You need to specify the type. And you just use it like that, yes. So it's not very difficult. It looks quite easy, yeah, just wrapping your function. There are some caveats here, and that's an example I quite like, and that's why I put this on the slide. So when you have a function that will do something random, it sometimes PySpark will actually try to optimize things for you. And this is why UDFs are considered deterministic by default. So let's have this easy function we have here. We just want to get a unique ID for some objects. And this is something that you cannot do with pure PySpark, yes? So as you can see, first I create just a small table and run the same function twice. And even though it's a random function, yes, we get the same result. In one row, we get the same result. It's not as bad as always giving us the same random ID. In this case, it just gives us for each row. Spark thinks, okay, I will optimize something for them. Since they call this function twice, I already know the result. So if your function is actually non-deterministic, you need to mark it as such. You can see it below. There's this method as non-deterministic. And it actually will produce random results this time. It will just rerun this function every time you want. So I told you a bit about optimization, about how bad performance is, but let's see how bad, yes? So all the experiments you will see were done on the cheapest Databricks cluster. So, but let's just look at the differences, yes? So here's a function that just works as pure PySpark, yes? So you just return a number plus a number. And here's our the UDF with no, and see the performance difference. It was run on around, I don't know, 10 million rows. Or 100. I don't really remember. Yeah, and you can see that the difference is pretty stark here. So what can we do to make it better? Because obviously people wanted to do it better from the get-go. And that title, Run Python Code with PySpark Fast, is actually stolen from the article that was introducing pandas UDFs. So you hear pandas, now that sounds a bit more familiar. And pandas UDFs were introduced in Spark 2.3. So when I mentioned I was waiting for this Spark 2.3 and they wouldn't install it on our on-prem cluster, that was one of the reasons. But they went through a big overhaul in 3.0 version. I will tell you more about it later. And they significantly improved the performance of UDFs. Why? Because I mentioned that the main cost was the transfer of data between JVM and Python. And here it was done using Apache Arrow. You probably heard of it by now, but just for those who don't know it. So it's basically a standardized language agnostic specification for your data that was created basically for this purpose, yes, for making the cost of moving data from one system to another, from one programming language to another, as easy as possible, yes? And here the serialization and deserialization costs are very low. But what's important for a data scientist is that within those UDFs, you actually work with pandas APIs. So let's see what it looks like. So similarly, we will create a pandas UDF. Yes, the comment says it will be done the way we do it in Spark 2.3. Because while it was quite nice to be able to finally do it, imagine that you have this function type and you need to track like 6 different function types. So people were initially very enthusiastic, but then they were like, that's a bit much, yes? So that's a lot of stuff to learn. So it wasn't as easy as with UDFs that you just had a decorator, return type. These function types were actually overlapping slightly, and knowing the names weren't very actually, like this scalar type doesn't actually return a scalar, yes? And a different type that returns a scalar is called grouped map, which is, yeah, probably not what we expected. But as you can see, what happens here, yes? So you got pandas UDF decorator, return type, function type, and now the function is the same, right? But now this V here is a pandas series, and the audio output will also be a pandas series, yes? So I mentioned the whole mess, and now if you run the code that's here, you will get a user warning if you're using Spark 3.0 or higher, because actually people working on introduction of Spark 3.0 decided like, that's too much, this is actually a mess, people don't understand what they are doing, people don't like it, people don't use it because they don't know which function type to use, yes, they don't use the whole extent of possibilities here. So there was this issue, there was community discussion, and the language changes to suit us better, especially since later Python introduced type hints, yes. So right now it works a bit different. So the modern way of actually specifying pandas UDFs, you just need the return type, and then you just use type hints to show what you are doing, whether you have series here or something else. And while I'm on that, let's see what we actually can do. So there's the series to series UDF, which just outputs like you input a column and it will output a column. It's the old scalar type. But there's like, you can output more than one PD series, like you see in the example on the bottom. So you use it then just putting those two column names as arguments. And there's one significant thing. So it's like you can think of it as a map, yes, because the input length needs to be the same as the output length, yes. So you cannot skip anything in your series. It just expects each entry to map to something. So people were started using it and thought that it's pretty much nicer than what was before, especially since they could just use all that pandas had inside. But data scientists were immediately there with their whining about models. So imagine, even though here you have a PD series, imagine that you want to initialize a model. Yeah, you load a model which is, I don't know, at best multiple megabytes, and you don't want to do this repeatedly, right? So what was introduced then was iterator of series to iterator of series. So here you have the classic example with S+1, and below you have the more typical usage, yes? So you load a model, and then you just keep reusing it for each series in the iterator, yes? Again, this is very useful when your initialization is costly. There can be something else. It doesn't need to be loading a model. But basically, most of the caveats remain the same. Yes, so you can input multiple series, you can output one series, and the input length needs to match to output length. Still not perfect, still not very versatile. And there was one more type which was used for aggregations, which I mentioned, like grouped ag is the type that actually outputs a scalar. And this is the sort of function that basically creates aggregations on your pandas series, yes? So it was mostly used for, like you see, either aggregating the whole data frame or aggregating with groupBy. And here the output needs to be a single value, and it needs to be one of the primitive data types. Okay, I haven't mentioned performance so far. I just said that people like the syntax, basically. So what about performance? And performance, let's add one more function to our examples. So the same function now as pandas UDF. And you can see that our pandas UDF is like 3 times faster than the original UDF. The bad thing is that still doesn't stand a chance against the original original PySpark version. But yeah, like how many of you are going to write a UDF to do something that can be actually done with PySpark, and for something that's like +1, yeah, probably nobody. So here's an example nicked from the origin, the paper introducing pandas UDFs. So this is an example using SciPy, and this is cumulative probability. This is very convenient because it both acts on a single number and it acts in a vectorized fashion on a whole series, or more like a whole array. So what do we have here? Like we have it returned as a float, returned as a pandas series, and here the performance is like the difference is more staggering, yeah? Because here we've got like 200 times better performance. I think in the original paper it was 300 times, but yeah, 200 times, I'll take it. Okay, but still, it's just only series, single values that you can return, and immediately people wanted to like output more stuff with their UDFs. So obviously the community of developers listened to them, and at first people were playing around a lot with stuff like just adding multiple outputs as arrays or whatever, but that's not very practical, right? Sometimes you want to play with the whole data frame. And yeah, so what else is there? Pandas function APIs. So they were introduced in 3.0 as it's still everywhere you look, it's marked as experimental API. But yeah, I think they are pretty safe to use. Again, they use Apache Arrow to transfer the data, and inside you use Pandas API to work with the data. And the logic is like very similar, but there's a main difference. You can just use a Python function as long as it, takes Pandas data frame as input, outputs Pandas data frame. This is fine. There's no need for any wrappers. Type hints are optional, though encouraged, so whatever. But this time it outputs PD data frame of arbitrary length and whatever shape you want. Though this comes with one downside, because instead of just specifying return type, you need to write the full schema of your output, which people don't really like doing. But what can we actually achieve with those functions? So first there was the grouped map that you used with apply in pandas. And as you can see, first let's look at the usage below. So you just grouped your data, and it's the familiar pattern like split, apply, combine. So first you split the data into groups, you apply your function, and then you combine it. It comes with its own downsides because all the data from a group needs to be loaded into memory. Again, something that data scientists don't really like thinking about, like memory, who cares? Like, we've got big data, we were sold this amazing solution to handle big data, but you will see that we actually need to remember that, especially if our data is skewed, yes? And this requires a full shuffle of data, which is again something that data scientists don't really think about. Like, they just want to see the results, then they don't know about the internal workings of Spark. So let's have a look at our function that we have here. So our function actually accepts PDF data frame and outputs a data frame. So here it's a very easy example because the schema is basically the same as the input schema is the same as the output schema, yes? So we've got like this ID and we return this double column. Okay, so so also the shape is the same, but let's now have a look at an example where the shape will be different. And that doesn't really, well, no, let's go back. Because here you got this groupBy and people immediately went like, I have groupBy and then I can apply a Python function in Spark. But I'm not grouping by anything. Can I still do it? And as I said, like, people didn't really care about grabbing all the data into memory, so they just did fake groupBys. They just did groupBy by nothing just to get this grouped data object. And the need actually was met with some supply here because we got map in pandas. So map in pandas is basically just mapping every batch in your partition and transforming it. Again, you can control the batch size, so you escape this problem with grabbing too much data that's not going to fit into your memory. But this one, which seems to be confusing to people, again works on iterator of now data frames. So you just work on it, producing an iterator. You can again make use of the lower initialization costs. And there is no no restriction on output length. As you can see here, we're doing some simple filter. So this obviously works with different output length. Okay, but these examples all seem like extremely easy and not like something you would ever actually need something better to do, right? You can filter your data in PySpark easily. You can add +1 to your data in PySpark easily. You can group here we had aggregation, maybe before we had aggregation, this can be done. This normalization probably would also we will be able to actually do it in pandas, in PySpark. So let's actually have a look at what people actually are doing with, as data scientists, and what they can do with PySpark instead of just grabbing the data and going to pandas. So first, let's have an example with scoring data frame with a stored model. And here it's a bit of code, but we actually load the famous iris dataset just so that it will work on your computer if you grab this code. And this function, the predict function, actually is designed the way that it will work on a pure pandas data frame, yes? As you can see, we actually can use the predict function on pandas data frame. We load our model, put our data frame as an argument, and it actually returns the data frame. Yes, pandas data frame with the iris dataset data and some columns like predictions. Here you can actually see that some of these are, here we have a number, here we have an array, here we have a string. So there's no restriction on what we actually output, yes? And let's see if it actually works, how to make it work in PySpark. So we create a Spark function, Spark data frame with create data frame from our pandas data. right now, like I said, that's the sort of big data that fits in an Excel. And I think fits on the back of your hand, actually, so it's not that much. But you can see first how difficult specifying the schema is, yes? I mean, you need to remember to grab the original fields. You need to specify, for each field, you need to specify the type because really PySpark is supposed to be able to guess, but it hardly ever guesses right, and usually just throws errors at you until you provide a schema. And as you can see, using it, writing a wrapper that will use the iterator is super easy. We again use the model, load model part, yes, as our costly initialization. And then we just yield predict for each of the pandas data frames in the iterator. And when you actually run this with map in pandas, let's show a couple of the results, and we get basically the same table with the right types. And here's honestly, I've never done this way. I'm just showing you here as an example of the map in pandas. But I have trained models using Spark to distribute it. Because imagine you have a lot of data that you really don't want to pull into the driver. And for example, here we have 8 groups of 10 million rows. So we can do quick maths. This is an integer. Here we got random, which is double. Here we got another double. So this is like 4 bytes plus x byte, which is 20. And times 10 million rows. Each of these groups is like 200 megabytes, which is reasonable to pull into one group on an executor. Yes, because I said this will be loaded in memory if you actually use the apply in pandas function I mentioned with groupBy. But imagine doing this for 8 times more data, or I don't know, 100 times more data, yes? If we had 100 groups here, it's not very usable, yes? So what we are going to do now is we're going to train some models on this data. So we got the random column, and then our output will, spoilers. Our output will be 40 times that random column and the ID column, so that we know that we actually trained the model for the right group. And we throw in some noise with the randn function, a bit of noise, just 1/10 of it. Here you can see the numbers, yes. So like I said, each of these groups will be around 200 megabytes, yes. And we use Spark to distribute training the model. And so just a simple model. We don't want to do anything fancy here. We fit the model with model fit. We calculate R squared for the model with model score. And as you can see, you just do it the way you would do it in pandas, right? It's not actually in any way complicated. And then we return a data frame. We grabbed the group keys that you can actually get from your groupBy, similar as you would iterate pandas, groupBy. It's very similar here. You can grab the keys if you specify them. And what then? We apply it in pandas. We will return the model ID as integer, coefficients, intercept as floats, R2 as floats, R squared as floats. And you can see that we specify this data frame here. And what we also did here was actually storing the model, yes, because you want the model to reuse it probably. And you can actually do it on your executor as long as you store it somewhere the executor can reach. So remember that in Spark there are transformations and actions, and none of this will happen until you run an action, right? So we run models show, all 8 of them, and we can check how well the models were trained. And as we can see, coefficient is around 42 everywhere. Intercept is 1 for 1, around 2 for 2, up to 8, which was somehow perfect. And our R squared is also very high, no wonder, right? So these were 2 practical examples, like especially the second part is very nice when you are actually doing some, if you want to actually train models for a lot of groups, a lot of data, and your data is actually somewhere where you collect it from with Spark. So to wrap this whole thing up, what we've learned today, so we've got the pandas, Python UDFs that we will forget about from now because we will start using the better pandas UDFs that are actually vectorized, that enable us to either make use of the costly initialization with iterators, or if we don't do this, we can just use series to series version. We can use them also for aggregation with series to scalar. And if we want to actually run something on the whole data frame, we've got the pandas functions API, which has map with map in pandas, which has grouped map with apply in pandas, and also co-group map that I didn't mention because it mostly works the same as grouped map. And I haven't heard of a lot of people using co-grouping actually. And I hope that at least some of you are convinced now to give those more specialized things a go and to move your pandas pandas pipelines, pandas things you actually did in pandas before to PySpark to let it parallelize it and deal with the big data aspect for you. Okay, thank you. So do we have any questions?
Yes, thank you very much. We have some questions. So the first question would be, does PySpark documentation cover the gotchas you mentioned? What is the best knowledge source on efficient PySpark?
I would say that it does cover those gotchas, but you need to read it. On this example here, you need to read all the way through and probably read the articles around it, like the officially published ones. But things, if there's something like, those inefficiencies and so on, they are usually mentioned. It's not something that's somehow super obscure or whatever. It's just that people don't really pay attention to it, in my experience, especially data scientists who don't want to really know or aren't actually given time to learn or resources to learn how Spark actually works internally. They are just told, it's Java underneath, and who cares about Java? Well, I do care a lot, but I do care a bit, but just a bit. The best knowledge source, I would say that Databricks itself publishes a lot of interesting articles. You can actually work through the PySpark documentation because they have some get started guides. But I found over the years that a lot of tutorials are just on the most basic stuff, like select this way, group by this way, you're done, But so it's more than you need to run into problems and then learn. And there's one very good book. Wait, I can actually tell you because I downloaded it for this purpose. Do I have it here? No? Yes, no? Okay. And it's called Learning Spark. I actually used it a bit here. Learning Spark, lightning fast data analytics.
It's not visible on this display.
Sorry. Wait, I will need to.
Yeah, like it's
Yeah,
close.
learning Spark, lightning fast data analytics. Yeah. And it's actually updated. Yeah, the second version covers all those features in Spark 3.0 that I've mentioned. Okay, let's maybe close it. You don't see any illegal books on my computer.
Great.
Okay. This is one that I really recommend.
Great, thank you very much. Next question. Pandas recently introduced an experimental arrow backend. Does it have perspectives for UDFs, like improved performance?
Yes, actually, because then the pandas underneath that you have, like the version of pandas that you use with PySpark will actually enable you to use this, right? But this, I don't think I've read anything about like the performance coupled with PySpark specifically, because it's still quite fresh.
Okay, thank you. Next question, why data scientists do not like schemas? It enforces structure on data that you need to perform further operations anyway.
Okay, I honestly love this question because I have no idea like why, but I've seen that people like this extra step is difficult for a lot of people who are used to work with Python that really doesn't, that allows you to get a lot get away with a lot when it comes to data types. And then with pandas that also is, there's no really, like there are D types in pandas, but people mostly work around them and not like embrace them as part of their workflows. And since a lot of stuff is actually done automatically when you load data in PySpark, people just don't know how to write it. And to be honest, I myself think that there's like a lot of things with like the schema. A lot of times you need to just write it from scratch. And if you have very complex data types, it can get boring quite fast. Yes, there aren't that many tools that help you with that, or maybe I just don't know the right tools. If you do, just write to me on my LinkedIn because I would actually like to do it faster.
Great, thank you very much. And the last question, was the model trained on cluster or driver?
The model would be trained on our executor, yes. So this isn't trained on driver. That's the difference, right? Because we don't drag the data to driver to train the model. We actually distribute it on our executor. So that's the biggest improvement that we have with this apply in pandas thing, yes? So the data is grabbed into memory on executor and then trained in Python, not on JVM, but on the executor. Okay.
Great, thank you very much. I don't think we have any more questions. Yeah, thank you for your answers. Thank you for the talk.